Okay, so our second speaker this afternoon is Professor Shoucheng Zhang from Stanford University, and he'll be telling us about his work in the area of topological matter.
Thank you very much for the introduction. It's a great honor to be invited to speak at the Kavli Symposium. I'd like to tell you, in the previous talk, you have heard about a particle, a wave, that has been looked for 100 years and was finally found. The story you're about to hear now is about a fictitious particle, a conjecture particle, about 80 years ago, theoretically postulated, and now there is strong experimental evidence for its discovery. The work I will report is a close collaboration between theory and experiment. On the left, you see a theoretical proposal where to find Chiral Majorana, namely in a topological insulator that has been magnetically doped and with a superconductor applied on top of it. And then we also predicted a very precise experimental signature for the existence of Chiral Majorana Fermion, namely in a half-quantized plateau. And that is the experiment that was carried out, and this is the experimental evidence for it. So let me tell you about the whole story. The story started with our hero, Paul Dirac. In his effort to unify Einstein's theory of special relativity with quantum mechanics, he wrote down the famous Dirac equation. When you go to Westminster Abbey in London, you can see his famous equation in the plaque. So in this effort, in writing down the Dirac equation, first of all, he noticed that the wave function is complex, but also he finds that there are two energy branches. There's a positive energy branch and a negative energy branch. And at that time was a great puzzle how to interpret the negative energy branch of the solution. And then finally he came up with the brave prediction that the negative energy solution actually means the existence of antiparticle. For every fermionic particle in the universe, he predicts there should be an antiparticle to it, which has almost the same property but the opposite charge. So he predicted basically the existence of a positron which have the same mass as the electron but have the opposite charge, therefore the name positron. Very fortunately, that theoretical prediction was confirmed experimentally only 5 years later. So Dirac was very fortunate in cosmic ray radiation. So since then, it has become a fundamental law of nature that for every fermionic particle in the universe, there exists an antiparticle. The antiparticle of the proton is antiproton. A neutron, even though it's electrically charged neutral, it also has an antiparticle, which is antineutron, which has the opposite baryon number as that of the neutron. But sometimes we pursue a theory by curiosity. And there was a great but somewhat elusive theoretical physicist, Chiral Majorana. And he was playing with the same equation that Dirac wrote down. And in the Dirac equation, it has 4 by 4 gamma matrices. Dirac chose a set of gamma matrices which has both imaginary and real entries. So therefore, the solution Dirac obtained is complex, and the complex conjugate of each other are interpreted as particle and antiparticles. But Majorana, somehow by simply playing around with this set of gamma matrices, he came up with a set of gamma matrices which are purely imaginary. So if these are purely imaginary, and if you have an eye here, he obtained a solution to the Dirac equation, which is purely real. If you have a real wave function, the complex conjugate is itself. So therefore, he made a brave prediction that there could actually exist fermionic particles which does not have antiparticle, or which is its own antiparticle. But unfortunately, at that time, nobody paid any attention to him because almost every particle there was an experimental discovery of the antiparticle. And he was somewhat disappointed. And on a ferry trip from Naples to Palermo, he disappeared and was never found again. So ever since then, it has been a deep, deep mystery in physics. One about Majorana particle, whether it exists in nature, and the other is about Majorana himself. This story happened exactly 80 years ago. The property of Majorana, even though I told you that neutron cannot be a Majorana particle, it has antineutron has been discovered as the opposite baryon number. But neutrino has been conjectured to be a Majorana particle. In fact, in the standard model, neutrino is a chiral particle which does not have a mass. But that contradicts with the later experimental finding that neutrinos does have a mass. But the only sensible mass term, theoretically, we can add to the neutrino is actually a Majorana mass term. So that's actually the existence of mass for neutrino. It gives us a very good indication that neutrino might itself be a Majorana fermion. Theoretically, Majorana fermion is a very deep concept. It's essential for formulating the concept of supersymmetry. So there are actually two ways to take half of a Dirac particle. If you have a complex solution, you can take the real part. If you have a purely real solution, so Majorana particle being real is in some sense half of a Dirac. There's another way to take half of a Dirac fermion. A Dirac fermion can be viewed as a formation of two opposite helicities or chiralities, but if you have a massless particle, which is purely chiral, it is another way to take half of a Dirac fermion. In different dimensions, there are different ways to take half of it. Sometimes you can impose a chirality condition, sometimes you can impose a Majorana reality condition. In very, very special space-time dimensions, you can impose both conditions at the same time, namely both the chirality condition and the Majorana condition, and that special dimension only exists in 1+1 dimension, one-dimensional space, and one-dimensional time, or 9+1 dimension. And the discovery I will report about today is exactly the case in 1+1 dimension. You notice these are special dimensions for superstring theory. String is a one-dimensional object. It sweeps out a 1+1 dimensional world sheet. It also lives in 10 dimensions, namely 9+1 dimension. The difference between these two numbers is 8, and the number 8 is also deeply profound in mathematics. This is called Bott periodicity. So theorists love this concept because it tells about some very intricate patterns, theoretical patterns. So now these are considerations mostly out of high-energy physics. For a broad symposium such as Kavli Symposium, I'm happy to make the connection between two different branches of physics, high-energy physics and condensed matter physics. But in condensed matter physics, Majorana fermion could occur as elementary excitations of quasi-particles of topological states of matter. And that's the central object of my talk today. But today, the special focus being focused upon Majorana fermion is because it's not only fundamental, but it could also be very useful, namely in topological quantum computing, which I'll talk about today. So in the previous talk, you heard about the search. So fundamental physics is maybe majority of it is focused on searching for missing particles, Higgs bosons, gravitational wave you heard from previous talk. Certainly Majorana fermion is on everybody's list, magnetic monopoles, axions, and dark matter particles. So today I will tell you about the experimental evidence for Majorana fermion. So what about in high-energy physics? How can we detect whether neutrino is a Majorana fermion or not? The proposed experiment is called the neutrino-less double beta decay. So if you look at a beta decay process, a neutron decays into a proton plus a neutrino plus an electron, and that is the standard beta decay process. But if you look at a double beta decay, another neutron is decaying into a proton plus an electron plus another neutrino. So normally, two neutrinos will come out. But if neutrino is a Majorana, it's its own antiparticle, then they give a possibility that you can view one neutrino as the particle and the other neutrino as the antiparticle, and then they can annihilate each other. So therefore, it will give you a process called neutrino-less double beta decay. And if you discover such a process, it will be a very strong experimental indication that neutrino is a Majorana fermion. But to the best estimate, this experiment is maybe 10 to 20 years away in the experimental effort, but we should still try. After all, from the previous talk, we heard something had been tried 100 years and finally worked. But in condensed matter physics, we can try to design tabletop experiments to discover Majorana fermion. And this is in the topological states of matter. So maybe you are all familiar with the quantum Hall effect. And this is the cartoon picture of a quantum Hall effect. So it is a state that breaks time reversal symmetry, and it is totally gapped in the bulk. It is a full gap in the bulk, but has gapless edge state. And has maybe the simplest possible you can imagine, namely one branch, dispersion branch, which is propagating in one direction upstairs and in the opposite direction downstairs. So this is called chiral fermion. So in one dimension, the concept of chirality is simply the directionality. If it goes only in one direction, it's called a chiral fermion. So this was discovered in the 80s by Klaus von Klitzing, and successive theory understood its topological properties. Altogether, 3 Nobel Prizes have been awarded in connection with quantum Hall effect. So in the year of 2005 and 2006 and 2007, we came to the realization of the quantum spin Hall effect, which is a system that preserves time reversal symmetry, and it's fully insulating in the bulk, but has gapless edge states, but this time with both branches, both the forward propagating branch on one edge and the opposite propagating branch in the opposite edge. But these 2 branches meet at one point, namely k equals to 0 point, which is a time reversal invariant point. And that degeneracy of a crossing is protected quantum mechanically by the Cramer's theorem in quantum mechanics, which enforces that in a spin 1/2 system, you have to have such double degenerate points. So therefore, this is a topologically protected state. So to all these, and this has been experimentally discovered, as I will tell you about just a little bit later, but to all these insulating bulk states and gapless edge states, there are superconducting counterparts. So one famous example is if you can imagine a 2-dimensional superconductor, spinless, that's paired into p plus ip. If I have spinless fermion, they cannot pair into S wave. The next state they can pair into is a p plus ip state. So that would be fully gapped in the bulk. P plus ip would also break time reversal symmetry, but then it will also have a chiral fermion, which propagates only in one direction. Only difference between this state and that state is that this is a superconducting state that does not conserve particle number. It only conserves particle number modulo 2. And therefore, this can be a Chiral Majorana Fermion. Namely, in here, I have both a particle branch positive energy and a whole branch negative energy if the Fermi level is at 0 energy. But here, I only have one branch that there's no longer any distinction between particle and antiparticle. So this is half of that, which is half of that. So this is 1/4 of that. So these topological states of matter are extremely, extremely interesting if we can discover them theoretically. And this has been the holy grail that condensed matter physics has been looking for. So today I would like to take you to a journey, how to arrive at that state, which I claim is 1/4 of that, by starting from a state of topological insulator, introducing magnetic doping to go to from quantum spin Hall to quantum anomalous Hall, and then applying on top of it an ordinary conventional superconductor, which I claim will bring you to this holy grail state we have been looking for. So let's start the journey. And so we start with this idea of topological insulator. This is a chart of binary semiconductors plotted in the space of energy gap and lattice constant. And so we were looking for this kind of topological state, and we were wondering where to find them. And one day I was looking at this chart and noticed there's something very strange and remarkable about this chart, that this energy gap, which normally everybody take to be positive, there's one member in this chart which has a negative energy gap. And that's the material called mercury telluride. And we came to the realization that this negative energy gap means topology, that this is the interesting new material, which is topologically non-trivial compared to all these materials, which has positive energy gap, which is topologically trivial. So this is the science paper we published in 2006, which predicted the first topological insulator in nature. But not only we predicted one material, we predicted a principle, namely the principle of band inversion introduced by spin-orbit coupling, leading to a negative energy gap or band inversion. And since then, every topological insulator has been predicted. So if you contrast this field with superconductivity, almost no superconductor has ever been predicted theoretically, but almost all topological insulator has been predicted theoretically. So if you look at this chart, mercury telluride sits here. Cadmium telluride has almost the same lattice constant, but has a positive energy gap. So therefore, you can make these sandwiches where the breads are the cadmium telluride and the cheese is mercury telluride. And this is the beautiful experiment done by Lawrence Molenkamp's group in University of Würzburg in Germany in 2007 after our theoretical prediction. So you can make different thickness of the cheese. You can either make a thin cheese layer or a thick cheese layer of mercury. So then you, of course, predict that when mercury is very thin, the energy gap should most inherit from that of canyon telluride, which is normal band ordering, where S band lies above P band, and that is predicted to be an ordinary insulator. And then when you turn the Fermi level into the middle, the conductance is nearly 0. When you make the cheese layer thicker and thicker, and the critical thickness is about 6.2 nanometer in thickness, then this material first closes the gap, going from here to here, then reopens. But after it reopens, it brings into it, this material becomes band inverted, topological, and has this topological edge state. So then when you turn the Fermi level into the middle of the gap, you still intersect those gapless edge states, which can do conduction for you, and that's predicted to have 2 e squared over h conductance, and that was experimentally observed. So this is the story of the discovery of the parent material, which I will successively build upon, namely the discovery of the topological insulator. So afterwards, there are theoretical predictions, both in concept and in material, of the 3D topological insulator. And our group actually predicted by now a very, very popular 3-dimensional topological insulator in the material system of bismuth selenide, bismuth telluride, antimony tellurium. But in another member of the group of 4, which are similar, this member, when you look at the periodic table, has the lightest elements among all 4, and therefore this was predicted to be a normal insulator, whereas all these two are predicted to be topological insulator. So 3-dimensional topological insulator have a conduction band and a valence band, but then they have a 2-dimensional Dirac cone on the surface of this material. But then we start to ask ourselves the question, what happened? So we all say that this point, the Dirac point, is protected by the time reversal symmetry. But what if you break time reversal symmetry on purpose by introducing magnetic dopants onto the surface? So if these magnetic dopants form a ferromagnetic ordering on the surface, then the time reversal symmetry is broken, then there's nothing that protects this Dirac point, and naturally a gap will open up on the surface. So on the surface here, if you have a ferromagnetic domain, which has well-ordered ferromagnetic moment, a gap will have opened up. But what if you have ferromagnetism in another domain which pointing down? So that would also have a gap. But what about on the domain wall? That is the question we ask ourselves, and the answer is extremely interesting. So on that domain wall, there lives a gapless state, which you might have guessed, because here the magnetization will be 0. So it's more like the case with time reversal symmetry. But very interestingly, not only it's one gapless mode, it is chiral gapless. It has a unique propagating direction defined topologically by the vector cross product between the surface normal and the magnetization gradient. So by the right-handed rule, it gives you one unique direction where they can propagate. So if you turn this picture around, namely having a 3-dimensional topological insulator, where on the top you apply magnetization up, and on the bottom you apply also magnetization up, uniform magnetization. Then you notice on the top, the magnetization direction is aligned to the surface normal, but on the bottom, the magnetization is opposite to the surface normal. So that will make the 4-side wall look like magnetic domain wall. So there will be one chiral branch which will propagate on these 4-side surfaces. And that is the prediction of the quantum anomalous Hall effect. So Duncan Haldane in the 80s wrote down a model which has quantum Hall effect without external magnetic field. But that was a tall model, which is very interesting for theoretical study. But we proposed actual mechanism for realizing the quantum anomalous Hall effect by magnetization introduced to topological insulators. Another cartoon picture to understand the effect is that if you have those spin paired state in a time reversal symmetry system, once you introduce magnetization, they naturally go into a state where one branch is destroyed, the degeneracy between the red and blue is broken, the blue can be more extended into the bulk, and they can annihilate each other, leaving only the blue. So this is the mechanism to go from quantum spin Hall topological insulator through magnetic moments into quantum anomalous Hall. And that effect, after a theoretical prediction of concrete material, was a theoretical collaboration between our Stanford group and the IOP group. and then a further experimental collaboration with Chiral Majorana's group in Tsinghua University. So this is the completion of all the quantum Hall trios. So there's the classical Hall effect, the classical anomalous Hall effect, the classical spin Hall effect, but to all these three classical Hall effects, there are quantum counterparts, the quantum Hall effect, the quantum spin Hall effect, which we observed in 2006, 2007. Now finally, the quantum anomalous Hall effect. So this is really an exciting moment to celebrate in the history of condensed matter physics, a search that has lasted also maybe even longer than the search for gravitational wave, namely the completion of the table of all 6 Hall effects, the 3 classical Hall effects and 3 of their counterparts. So in this plot, the Chiral Majorana's group in Tsinghua University basically studied magnetically doped, which is chromium-doped bismuth telluride material, and by sweeping the external magnetic field, a very low value of external magnetic field, even at 0 field, you see a quantized plateau at 1e²/h. So hence the name quantum anomalous Hall effect. Now let me move to the central part of my talk, which is the Majorana Fermion and the Majorana zero mode. So when I showed you on the second slide the Majorana's wave equation, that wave equation describes a propagating particle or wave that propagates in space and time. But later people generalized this concept even to not only a continuum state, but also a zero mode or a bound state in quantum mechanical sense. So there can be one quantum mechanical level, which is called the Majorana zero mode, which is exactly at zero energy. And this is the concept generalizing the continuum propagating state to a bound state, which exists exactly at zero energy. And there are a lot of pioneering work leading up to that, starting from Kitelev's theoretical toy model, and then with the theoretical proposal to realize these in nanowires, semiconductor nanowires in proximity contact with superconductors. It could also be realized if you have a 2 + 1 dimensional chiral superconductor in the vortex state. You can also realize this Majorana zero mode. And the way to detect this experimentally is through STM experiment by looking at the IDV to see if there is a zero bias peak. Now, if there's a Majorana zero mode, you indeed should see in STM a zero bias peak. Not only the peak should be located at 0, Patrick Lee and his group has predicted that a smoking gun signature is that the amplitude of the IDV at a peak should be quantized at 2e²/h. But if you have many nearby states nearby, that value will be reduced. So there are a lot of exciting experimental development in the nanowire case, in the STM on the surface, and in various superconductor systems. The problem has always been that a zero mode has been detected, a zero bias peak has been detected, but the IDV peak value has always been very small. But recent experiment has been more encouraging, but I would say maybe it's still not finally settled whether we really converge to the 2e²/h peak value. So that's to give background information and to give credit to the work which has been done before. Now let me move to our platform, and the whole idea is to start from the 2-dimensional topological insulator, some thin layers of bismuth telluride, then introduce some magnetic dopants such as chromium, and then adding a superconductor on top of it to see if we can realize Chiral Majorana Fermion. So the idea was first proposed in a theoretical paper in 2010 of such a device, of a quantum anomalous Hall state, such as chromium-doped bismuth telluride, but on top of it, a conventional superconductor. Why is this an interesting system? Now, if you have one edge state of the quantum Hall effect, which is a complex chiral fermion, it can always be mathematically decomposed as 2 Chiral Majorana fermion. That's just a mathematical representation. And these 2 Chiral Majorana fermion will be strictly degenerate with each other. But the picture will change. If you put a superconductor on top of it, then the particle number is no longer conserved, and then the degeneracy between these 2 Chiral Majorana fermions will be removed. So the blue Chiral Majorana will be different than the red Chiral Majorana. So now if I try to induce a plateau phase transition from nu = 1 to nu = 0, in the proximity contact, usually they will jump from nu = 1 to nu = 0, because these 2 are strictly degenerate. But now if I put a superconductor on top of it, this degeneracy is broken, and once the degeneracy is broken, the most natural transition is to go from 2 Chiral Majorana to 1 Chiral Majorana, and then to 0. So therefore, we predicted that without any fine-tuning, this is the most generic behavior that can happen. When you make a quantum Hall plateau transition from 1 to 0 in proximity with a superconductor, it always have to go through an intermediate phase, which is the holy grail, namely 1 Chiral Majorana. So you notice that I can always decompose a complex number into 2 real parts. Anytime you see even number of Majorana, it's not interesting. Anytime you see odd number of Majorana, then it's really interesting. And that, we predict, can be naturally realized in the plateau transition as an intermediate phase when it's proximity coupled to a superconductor. Then you may say, why not do it for ordinary quantum Hall effect? But the ordinary quantum Hall effect requires a very large external magnetic field, which may destroy the superconductor. So the discovery of quantum anomalous Hall in magnetically doped topological insulator is very timely. Then you can have relatively low magnetic field and then still realize the whole setup. So this is the idea. But then once you have these novel states, what is the smoking gun? What do you look for to prove that you experimentally found it? And that's the analysis we gave in the second paper in this series in 2011. So in this novel case, where 1 Chiral Majorana propagated through and the other Chiral Majorana is being fully reflected, you can look at the full conductance matrix. Because even though I have a superconductor here, conductance is still well defined because the incoming and the outgoing states are in the quantum anomalous Hall region, which totally preserve particle number conservation. So now you need to be careful in analyzing this problem. You have to look at the normal transmission, normal reflection. But because you have the superconductor on top, you would also have the undrift transmission and undrift reflection. But if you put all these things together, we predict that in this novel intermediate phase, you get a sigma 1,2 conductance of 1/2 E squared over H. Now that is something you might have guessed without doing any calculation. Because ordinary fermion, complex fermion, have conductance plateau quantization 0, 1, 2, 3. Majorana fermion has no antiparticle, so in some sense, you are decomposing a complex number into 2 real parts. A single Majorana fermion is half of a complex fermion. So therefore, it's very natural that they have conductance 1/2 E squared over H. And that we predicted is the smoking gun that you should look for. So we proposed finally in this paper with the full experimental setup how one should carry out the experiment, namely having a substrate, having a magnetically doped topological insulator such as chromium doped bismuth telluride, then with the ordinary superconductor applied on top, and then sweep the external magnetic field to look for this half plateau quantization. And this is the illustration of what is predicted theoretically in our this paper. Yeah. So then we started a collaboration with Professor Ken Wang's group at UCLA, and then with which grew the quantum anomalous Hall device, and then with Professor Kai Liu's group at UC Davis, which applied the niobium superconductor on top, and then also with Professor Jing Shi's group at UC Irvine, which did some of the initial measurements. So the material is chromium doped bismuth antimony telluride. This mixing ensures you the Fermi level is very close to the Dirac point. Then once you put the chromium at the Dirac point, a gap opened up. And then you apply this niobium superconductor on top, and here's the control device. So in the control device, you see the quantum anomalous Hall as you sweep the external magnetic field, and then you have the 1 plateau, and then also the 0 plateau, and the -1 plateau. By the way, the 0 plateau was also theoretically predicted by our theory group, and there are many experimental confirmations of that. So this is the pure quantum anomalous Hall device. What happens when you apply a superconductor on top, a sputter niobium on top of this device? Then when you measure the conductance from 1 to 2, here is the experimental sweep as a function of external magnetic field. So it has this 1 plateau, it has something close to the 0 plateau, then it has this predicted 1/2 plateau. And this 1/2 plateau is more pronounced when magnetic field is small, less pronounced when magnetic field is large, consistent with the picture that, of course, superconductor is weakening magnetic field is weakening the superconductivity, weakening the proximity effect. So that was a very exciting discovery, and the experimental group did a heroic job on that. But then the referee came back actually we anticipated this question, but the referee came back with a trivial explanation of this effect. They say, well, 1/2 plateau sounds interesting, but what about a trivial explanation? That this superconductor is first of all acting just like a metal to the lowest order. And then if you have a metal, then you're basically shorting. You basically have a quantum anomalous hole here and another quantum anomalous hole in series with each other. And if you put this one E squared over h, another one's E squared over h in series, according to the resistor rule, you naturally get 1/2 E squared over h. What's the big deal about that? So this actually is the possible trivial explanation. But if this were the explanation, then you can never explain the 1 E squared over h plateau, because the metal is always there, and then you always have 1/2 E squared over h. But experimentally, you see both 1 and 1/2 and 0. So first of all, this is not a viable explanation. But that motivated further experiment. Namely, at much higher field, when superconductivity is totally destroyed, then this picture should be true. So there should be a reentrant behavior of starting from 1/2 at weaker field. At larger field, you go to 1, but a yet larger field, when superconductivity is completely destroyed, you should go back to 1/2. And the beautiful experiment carried out indeed verified this is true, that you start with this weak 1/2 plateau. At higher field, you see 1 plateau, but at yet higher field where superconductivity is totally destroyed, this trivial explanation does apply. But the very existence of this 1 plateau shows that here it cannot possibly be true. So then we also did further theory work in predicting what could be the 3-terminal conductance. Here we are just measuring grounding 3, measuring conductance 1 to 2. But what about grounding 2, measure conductance between 1 and 3 on top of the superconductor? And theoretically, in this non-trivial phase, we predict these 4 peaks. But in the trivial explanation, you only see this picture. And experimentally, it also comes out to be this case. So then let me briefly remark that this plateau is not quantized as accurately as the quantum Hall plateau. Quantum Hall plateau is experimentally accurate in low temperature. But here it's only algebraically accurate, that it will receive an algebraic correction at finite temperature proportional to t squared. It also has a finite size correction, but the finite size correction is very small due to the goldstone modes inside the superconductor. But even for 1 micron size device, this correction is 10 to the minus 6. The device experimentalists have used is 0.5 millimeter, so finite size correction is not important. So basically, after 80 years of intensive search, not as long as the gravitational wave, but still 80 years, we believe that there's really smoking gun evidence for chiral Majorana particle, thanks to these intensive theoretical and experimental work. But now let me move on to tell you what it could be useful. So first, it's an interesting and curious experimental and theoretical discovery. So first of all, when you, and then I will bring to the subject of quantum computing. So if you have chiral Majorana modes, it necessarily implies a Majorana 0 mode. Propagating chiral Majorana on the boundary as an edge state, when I thread a pi flux through the system, it necessarily implies a Majorana 0 mode. Maybe I skip that. But then let me move on to the topic of topological quantum computer. So quantum computer can do magic things because quantum mechanics operates in parallel. At one given time, 1 particle can go through 2 slits at the same time. This leads to the idea of quantum computer, but a quantum bit is notoriously unstable. And that leads to the idea of topological quantum computer. Maybe if we will have these kind of Majorana 0 modes, and if we can braid them around, we can actually make a quantum computer which is topologically robust. And there are a lot of pioneering works in this respect using Majorana 0 modes. First of all, we need to prove they really exist. But braiding them is actually very, very, very difficult. So we have now a new approach. When you look at our device, this is the very device in which experiment shows 1/2 plateau. I would like to make a new claim, which is very, very essential to this subject. Namely, this device, without doing any further work, is braiding by itself. So I invite you to look at the following picture. From lead 1, I inject 1 chiral fermion, which can be viewed as 2 chiral Majorana. But in the novel state, 1 chiral Majorana went through to the second lead, but the first chiral Majorana went back. And the same thing occurs here. Here I inject 1 chiral fermion, but it splits into 2 chiral Majorana. 1 goes through, and the other went back. So if you look at the space-time diagram of these chiral Majoranas, from lead 1, gamma 1 start from lead 1, went back to itself. Gamma 2 start from lead 1, but went to lead 2. On this side, gamma 3 started from lead 2, but went to lead 1. And gamma 4 start from lead 2, but went back to lead 2. So this is the space-time diagram of the propagation of these chiral Majorana particles. But when you look at this, it's a beautiful picture of a braiding between these 2 chiral Majorana. So this very rather artificial-looking picture trying to braid the Majorana zero mode, which is very, very difficult to realize, becomes naturally realized without doing any additional work in our device, which is braiding by itself. So therefore, this device is already operating like a Hadamard gate, that if you inject 1 fermion into the lead, into the wave packet, which can encode quantum information, whether the wave packet is occupied or unoccupied, then it has a half probability amplitude to go back to lead 1, or half probability amplitude to go back to lead 2. So if you trace this fermion, it's as if you performed a Hadamard gate operation from the North Pole back into the XY plane. And the fact that it went to XY plane is topologically protected. But what we measure experimentally in the half plateau is only a probability, not a probability amplitude. Even though you can give this nice interpretation, it's not a proof. In order to prove, you really have to show that this is a probability amplitude rather than a probability, which you already measured. And that is the new idea which we published in this paper, posted in this paper. Namely, you have quantum anomalous Hall going to a superconductor, going to a quantum anomalous Hall with lead 1, lead 2 here. But here, you can apply a gate voltage in the quantum anomalous Hall region, which will add a phase to the chiral fermion, which is propagating. And then you reconnect this side with this side, which will give you a Corbino geometry. So this is the new device we propose, which is still theoretically proposed and not yet experimentally realized. Basically, this picture of adding a phase to this whole device, but connecting these 2 sides back to itself, giving you this Corbino geometry of a quantum anomalous Hall with a superconductor applied on top of it. So then this device repeats by itself, and then here by a gate voltage, you can tune the phase. So therefore, this whole device is doing the following operation on the Bloch sphere in the quantum information sense. You start with the injection fermion on the North Pole. By going through the superconductor, you rotate into the XY plane. But by this gate voltage, you make a further rotation about the z-axis inside the XY plane, and then you collapse it back again. So finally, you still measure probability, but because you operated a phase gate in the middle, it is like a Hadamard, phase gate, Hadamard, and back again. So experimentally, theoretically, you will predict that there will be an oscillation pattern between the conductance from lead 1 to lead 2 as a function of the gate voltage, and it will oscillate. And that oscillation is the interference fringe that will uniquely prove that you are measuring a probability amplitude rather than a probability. So I feel really we're in a very exciting moment that finally, I think, topological quantum computer can be possible. And the device is very simple. This is a 0.5 millimeter size device, and all the gates, and only thing you need to do, no funny business of braiding them almost by hand, but just by applying some ordinary voltage lead, there's not even any magnetic field, and measuring currents through leads, which we know how to do well, and as a function of gate voltage, we can realize topologically protected quantum gates. We prove braiding, we prove topological qubits. So at this very exciting moment, half-jokingly, I coined this particle to be angel particle. Inspiration comes from Dan Brown's book, Angels and Demons, Good and Evil, Positive Particles and Antiparticles. So in this story that terrorists stole some antiparticles out of the lab and they tried to destroy only with 1/1,000,000th of a gram. The effect is like a few tons of TNT. So for every particle, there's antiparticle. For angel, there's demons. But now we found a particle which has no antiparticle. So it's as if we have discovered angel particles, which has no antiparticles, only angels and demons. But I hope that they can really greatly, these angels can greatly benefit human society by making quantum computers possible. Thank you. One or two questions? Yes. Yeah. Yes. Yes. So we claim that this device already we give a precise geometry, that it's proving the braid. And the experimental evidence is through this oscillation. Very well defined, yeah.
Wonderful talk, thank you. When do you think the first one will be made, built?
So this experiment has already been done. You can only judge that this experiment doesn't look that different from that. So I think in a matter of 1 or 2 years. And the geometrical size is 0.5 millimeter, so no special processing needed. Yeah.
Can you comment on the advantages of using a topological quantum qubit over using something like a semiconductor qubit or a quantum dot?
So first of all, already this very advanced field of quantum computer is classified to be conventional quantum computer versus topological quantum computer. In a conventional computer these days, I read every day I hear some news, more qubits being built. But the key important number to pay attention to is the ratio of error correcting bit versus one useful bit. And that ratio ranges from 10 to 100. The most is actually, 100 is actually median. Some more pessimistic estimates is 1,000. So for one useful qubit, you have to build 100 error correcting qubit. That is simply not scalable. Topological quantum computer promise one qubit is just one qubit. Topology, this is the wonderful thing about topology, error corrects by itself. Now there's a distinction between what may be commonly referred to as the Microsoft approach, braiding the zero mode, versus the Stanford approach, which braids the Chiral Majorana Fermion. We estimate our approach is 1,000,000 times faster.
Thank you very much.
Yeah.
Hi, thank you for the talk. So I have a quick request. Can you comment on the bulk? So like the one that you're talking is actually the
so the bulk must be pretty insulating if you see a plateau which is pretty well developed at 1/2. So otherwise, it will not be at 1/2. Okay. So we're quite confident that the bulk, and this is the wonderful material science. If you remember our theoretical prediction of topological insulator, if you mix them, bismuth antimony telluride, you can tune the Fermi level very close to the Dirac point with no bulk states. And then chromium opens up a gap. Okay.
In the world line picture, how can we know the initial time and the final times are the same?
Very good, very, very good. Yeah, so here we only did, in the experimental measurement, it's a static measurement. And in order to build a quantum computer, you need to build some quantum dots here to sense whether one particle went through or not. And that defines the qubit 0 or 1. But the Fermi velocity is very well characterized. If I know the geometry, I will know the timing very precisely. It's about, Fermi velocity is about 1/100th of the speed of light. This is the reason why our device is very, very fast. It operates at basically at a speed of 1/100th of the speed of light. Whereas if you try to do some mechanical braiding, it will take forever.
Yeah. Thank you.
So this is really a new idea in the field of topological quantum computing.
So we know that Majorana zero modes are not abelian ion. So But how about the Majorana, this chiral?
Yeah, so this experiment will prove they're non-abelian braiding.
So even like this chiral Majorana,
yeah, it's a non-abelian. Well, it has something to do with the definition, but this experiment is the smoking gun. If you see the oscillation fringe pattern, it proves beyond any reasonable doubt that these are doing non-abelian braiding. Okay, thank you.